In 2021, a payments company discovered that their payment records and accounting records had quietly diverged over several weeks. Individual records in each system were correct. The two systems disagreed about which payments had been settled and which had not. The root cause was a design assumption that turned out to be wrong. The operation that settled a payment needed to update two things: a record in the payments database and an entry in the accounting database. The engineering team had wrapped both updates in what they described internally as a transaction. What they had actually written was two separate transactions, one in each database, executed sequentially. The first completed. If anything interrupted before the second ran, the payment was settled, but the accounting entry was never written. Both databases were ACID compliant. That guarantee ended at each database boundary. It did not reach across the gap between them. Consistency scope is the boundary within which a consistency guarantee holds. Every consistency guarantee has one. An ACID transaction is consistent within the boundary of a single database transaction. A foreign key enforces referential consistency within a single table relationship. A check constraint applies to a single row in a single table. A distributed consensus protocol maintains consistency within the cluster it manages. The guarantee does not extend beyond its scope. Past that boundary, the guarantee does not apply, and the system does not always make that boundary visible. This matters because scope is often narrower than engineers assume. It is easy to think of a well-maintained database as a consistent system. That understanding travels into every operation that touches it. Even operations that cross boundaries, the guarantee does not cover. The consistency property is not attached to the database as a whole. It is attached to specific operations, under specific conditions, within specific boundaries. The operation that stays within one transaction on one node has the guarantee. The operation that spans two databases or two services does not, regardless of how consistent each individual component is. Limits exist because extending consistency scope has a cost, and that cost grows as the scope grows. Keeping a single row consistent is nearly free. Keeping a transaction consistent across many rows requires locking. Keeping two databases consistent with each other requires coordination, two-phase commit, distributed locking, or a consensus protocol. Each of those options costs latency, reduces availability, or both. At some point, the cost of extending scope exceeds what the system can afford. That is where the scope ends. The limit is not arbitrary. It is the point where maintaining the guarantee would break something else the system depends on. 3 scope boundaries account for most production failures of this kind. The first is the cross-database boundary. A single ACID transaction cannot span two separate database instances. This is one of the most frequently violated scope assumptions in practice. Microservice architectures routinely place related data in separate databases, by design, to achieve isolation and independent scaling. The trade-off is that operations requiring consistency across those databases cannot use a single transaction to get it. Each database provides its own guarantee within its own boundary. Nothing provides a guarantee across both. The second is the service API boundary. When one service calls another to coordinate a state change, the consistency guarantee does not travel through the API. Service A can commit its own changes. Service B can commit its own changes. Whether both commit, or only one, or neither, depends on coordination logic that neither service provides on its own. An API call is not a transaction. A successful response from a downstream service does not mean the overall operation is consistent. The third is the read path boundary. Write operations on a primary node carry the consistency guarantee. Read operations routed to a replica, a cache, or a read-optimized store are outside that guarantee. The write path and the read path frequently have different consistency scopes, and in most distributed architectures, they do. Engineers who assume reads carry the same consistency properties as writes are assuming scope extends further than it does. 3 approaches manage cross-scope operations. The first is staying within a single scope wherever possible. The most reliable way to keep two things consistent is to make them one thing. In the same database, the same table, the same transaction. This is not always achievable. Scale and architecture requirements push data apart, but where it is achievable, it is the right call. Cross-scope consistency is always harder and always less reliable than in-scope consistency. The architectural decision to separate data should be made with that cost clearly understood. The second is the outbox pattern for cross-service coordination. When an operation must update two services and both updates must eventually succeed, the outbox pattern provides a reliable mechanism. The first service writes its own update to its database. In the same transaction, it writes a record of the pending second update. A separate process reads that record and delivers the second update, retrying until it succeeds. The first update and the intention to perform the second are always consistent because they were written together in a single transaction. The delivery of the second update is reliable because it never stops trying. The third is scope mapping. For every critical operation in your system, identify which consistency scope it operates within and where it crosses a boundary. The format is less important than the act of making the boundary explicit. Cross-scope operations should be visible, named, and understood. The failures that happen at scope boundaries are almost always failures of visibility. Nobody knew the boundary was there. Once boundaries are mapped, cross-scope operations can be designed deliberately, rather than discovered through incidents. The payments company resolved the divergence by replaying settlement events from a transaction log and rebuilding the missing accounting entries. They replaced the sequential dual database write with an outbox pattern. The payment record and the pending accounting entry were written to the payments database in a single transaction, and a separate process delivered the accounting update with retry logic. The two databases had been consistent within their own boundaries for years. Nothing had ever guaranteed they were consistent across both. Consistency scope is not a property of a system. It is a property of an operation. The same database that provides strong consistency for one operation provides no guarantee for another, because the second operation crosses a boundary, the first one does not. The failures do not happen inside the scope, they happen at the edge of it. Knowing where your guarantees end is not a secondary concern. It is the same question as knowing what your guarantees are.